Right, hello. If I can just emphasise, go back to something I've mentioned before. This way of transforming fractions. Say something like that. Okay, these are equivalent fractions. I mean, you can see. Hopefully, you can see this is true anyway. I mean, if you had a cake split up into eight parts, all 8 equal parts, and you took 4 of them, then you could hopefully see that you've got together you've got half a cake. So I mean that's consistent with what you've got here. So just to sort of emphasise what I've said before, that you can alter a fraction by dividing top and bottom by the same number. So if I divide the top of that by 4 to give me 1, and the bottom by 4 to give me 2, that's consistent with what I've just said. And sometimes I can work the other way as well. I need to work the other way, so I can multiply that by 4 to give me that, multiply that by 4 to give me that, and that's acceptable operation. I mean, it's very straightforward on a simple fraction like this, but I mean, if you're having problems on this, you can just go through them systematically. You don't need to do it in one go. I mean, I could say, okay, I'm not too sure, I mean, this is just for the sake of the example. I can say, okay, I'm not too sure here, so I'll try 2. Does the top and bottom divide by 2? Well, it does, so I can say, okay, divide that by 2, that'll give me 2. Divide that by 2, and that'll be 4. And then I look at it again and say, well, 2, does 2 go into top and bottom? Yeah, it does. So I divide that by 2 to give me 1. I divide that by 2 to give me 2, and that's that'll give me half. Can I go any further? No, I can't. But in a larger number, you can go through this systematically. You can say 2, and does top and bottom divide by 3, and then you go on to, well, it'd be 5, because if the top and the bottom does not divide by 2, then it's not going to be divided by 4 or any other even number. So I can go from 3 to 5, then to 7. I can ignore 9, because if top and bottom does not divide by 3, then it won't do. 9 will not be a factor either, so you go on to 11. I mean, that in practice you won't need to go on to that as high as 11 or so on, but I'm just trying to explain the general procedure. If the number should be so large that you're not too sure straight off. Right, so just having emphasised that, I want to mention a new rule, which is if I have something like, say for example, 4 times 2 to the power 5, what that is 2 to the power 9. What I've done here is I've just added the indices. I need to stress here that that's on the same basis that these bases are the same. Because that's a 2 and that's a 2, I can just add the indices and get that. If that was 2 and that was a 4, for example, or something, I wouldn't be able to do this. But because they're both 2, this rule works. And again, it's not too difficult to show how this works. If I just produce lower numbers for now, if it's 2 times to the power 3 times 2 to the power 2, which is sometimes noted as 2 squared, then using this rule, it's 2 to the power 5. How do I know that? Well, again, know what 2 to the power 3 is. I mean, again, I'm making a few assumptions here. Obviously, that's something I've just got to do along the way. I just have to assume that you know what 2 to the power 3 is. But if not, I'm going to explain it in this particular situation anyway. It's 2 to the power 3 means 2 times 2 times 2. And then if I bring this this multiplication sign down here, and then say 2 to the power 2, well, that's 2 times 2. Well, you can see that is 2 to the power 5. 2 times 2, that's what 2 to the power 5 means. 2 times 2 times 2 times 2 times 2. Right, so that rule, although it looks strange, it's fairly straightforward to explain how it works. If I was to use this in algebraic, I mean, we're leading up eventually at the end of the day to using algebra. I mean, but if we had an algebraic expression like this, I'm using a dot here to explain multiplication. Obviously, in algebra, I don't want to use the this sign because it's going to get mixed up with the x, which we normally use to denote an unknown. But I mean, that would just be that. That's what I'm stressing here. Is that on algebra, although some people typically like to think that algebra is hard, the rules for algebra are just using the same rules as for numbers. So if I can stress that here, you know, if you're okay with that rule and that rule, then you should be able to understand this rule straight off. And analogous to that, we've got a rule that says I don't know, I'm using algebra again. 2 to the power 13 over 2 to the power 9 equals 2 to the power 4. Okay, so that's an analogous rule where instead of adding the indices, I'm subtracting one from the other, just so long as I do it the right way around. And well, if I was to explain it simply, I mean, again, if I keep the numbers small, 7 to the power 5 over 7 to the power 2 is 7 to the power 3. Now, how would I could explain that? Well, 7 to the power 5 is 7 times 7 times 7 times 7 times 7, and that's over 7 to the power 2, that's 7 times 7. Now, remember what I just said, that you can divide top and bottom by the same factor. So I could say, okay, there's a 7 there and a 7 there, so I'll cancel that out. So I'll replace that by 1, okay? Again, this is one of those rules that you learn at the basic level. Once you've learned to the basic level, you can tend to ignore it. By that, I mean that we do normally replace that at the basic level, that is replaced by 1. But people tend to ignore that because at the end of the day, we've got to multiply this, and multiplying by 1 doesn't affect the result, so people tend to sort of just cancel out and just forget about it. But at the bottom level, what you're doing when you cancel out is that you're replacing it by 1. And I'll do the same here. So what I've got is, I've got 7 times 7 times 7, which is 7 to the power 3. I'll say times 1, which doesn't change it. So it's 7 to the power 3, and that's 1 times 1 now. So it's 7 to the power 3 over 1. So again, using the rule that we have applied before, 7 to the power 3 over 1 is just 7 to the power 3. Now, just bear with me a second. This rule is the type of thing that used to be used, or it relies on the basic of what of logarithms, which used to be a very popular device in the olden days for multiplying large numbers. So, for example, if I had something like this, 2 times 5 to 2, 4, 6, which equals 57810. Okay, so obviously nowadays you can just get your calculator out and do that straight off. Or obviously in the olden days you had to use long multiplication. But there is an alternative way of doing this, which is useful. I mean, obviously this is just, what I'm going to do now is just an example. Logarithms were useful for particularly larger numbers, maybe larger numbers than this. But I'm using this as an example of how it works. So that 235 would equal 10 to the power 3711. Okay, so again, if you know how indices work, 10 to the power 2 is 10 times 10, which is 100, and 10 to the power 3 is 10 times 10 times 10, which is 1,000. So a number in between 235, you'd expect it to have an index between 2 and 3. So that looks okay. And 246 is 10 to the power 2.3910. So if I use the rule that I've just said now, 10, that'd be 10 to the power 4.7621. So if I again convert that back to well, I say again, if I take that and convert it back to real number, that will equal 57823, I believe. So it's slightly in error. Basically, that's due to the approximations in the indices and so on. So it's slightly in error, but you can see that the basic principle behind it. Now, in the olden days, what you do, you look up in a log table, and this would be the log. That's the log. That's the logarithm of 235, and that's the logarithm of 246. So you look up those two figures, add those two logarithms together to get this figure, and then you would look back in a separate table of anti-logarithms to work out what this figure is. So we don't use this method nowadays because we've got calculators, but nevertheless, logarithms are still around. They are still useful, and I mean, you can have logarithms of different numbers. These are logarithms to the base 10. You can have logarithms to any number you want, really. And you've also got what is called a natural logarithm, which is probably denoted on your calculator by ln. The logs to the base 10 are normally denoted as log, whereas the natural logarithm is ln. And that natural logarithm has got many uses. Used in radioactivity, for example, so it has a connection to a real life situation. So logarithms, although we don't use logarithms nowadays, logarithms themselves are very much alive, and they are very much a part of the A-level mathematics syllabus. Anyway, again, as always, thanks if you're still with me at this stage, and cheers for now.